In the winter of 1955, deep within the frozen plains of Idaho, a group of military trucks rolled toward a fenced compound known simply as Test Area 5. Inside a hangar stood an experimental jet engine unlike anything on Earth. Its core wasn't fueled by kerosene, but by uranium. Thick walls of lead and boron surrounded it, and technicians watched from behind glass windows as engineers prepared for ignition. When the countdown reached 0, the air compressors roared to life. Valves opened, air surged through the reactor, and the temperature soared past 2,000 degrees Fahrenheit. Moments later, a deep metallic howl filled the test chamber. The exhaust shimmered blue, not from flame, but from ionized radiation. For the first time in history, America had built and fired a nuclear jet engine. It was meant to be the dawn of a new era, an aircraft that could fly for days, even weeks, without landing. But as the scientists soon realized, they had crossed a boundary few had dared imagine. The machine they created wasn't just an engine. It was a flying nuclear reactor, a weapon of endurance, and a risk no one truly understood. In the tense years following World War II, the United States found itself racing against an invisible clock. The Soviet Union had detonated its first atomic bomb in 1949, shattering America's monopoly on nuclear power. The new threat wasn't just ideological, it was technological. Every advantage mattered, and endurance was the next frontier. Conventional bombers like the B-29 and later the B-36 Peacemaker had range, but not enough. They could cross oceans, but not return without refueling. In a world balanced on the edge of nuclear war, that limitation was intolerable. The idea that would drive the next decade of research was born from a single, daring question: what if an aircraft never needed to refuel at all? If the destructive energy of the atom could be harnessed safely in a compact form, the sky itself could become a permanent launch platform. From this ambition emerged Project NEPA, Nuclear Energy for the Propulsion of Aircraft, established in 1946 by the U.S. Army Air Forces in partnership with the newly created Atomic Energy Commission, AEC. Fairchild Aircraft received the first contracts to study feasibility. Their early reports were astonishingly optimistic. Nuclear fission, they argued, could heat air directly to drive a jet turbine. Theoretically, a single pound of uranium could release as much energy as millions of pounds of aviation fuel. Engineers envisioned strategic bombers that could circle the globe indefinitely, always ready to strike. In Washington, such visions resonated deeply with a government desperate to maintain deterrence without relying on foreign bases. By 1951, the project had grown beyond mere theory. The Air Force formally restructured it into ANP, Aircraft Nuclear Propulsion, a vast joint effort with multiple industrial partners. General Electric took charge of the direct cycle reactor concept, while Pratt & Whitney explored the indirect cycle. The two approaches differed in philosophy. The direct cycle design would channel compressed air from the jet's compressor directly through the reactor core, heating it through nuclear fission before expelling it as thrust. It was simple, powerful, and dangerously radioactive. The indirect cycle, by contrast, used an intermediate heat exchanger, isolating the reactor from the airflow but at the cost of added weight and complexity. At the same time, Oak Ridge National Laboratory, birthplace of the Manhattan Project's uranium research, became a center for reactor development. Scientists there experimented with zirconium hydride as a moderator, a material capable of slowing neutrons efficiently without adding excessive bulk. Metallurgists faced new challenges: how to contain a core that would reach temperatures above 1,500 degrees Fahrenheit, and how to shield crew members from lethal radiation without grounding the aircraft under its own weight. The Cold War's early atmosphere encouraged bold risks. In 1953, the Air Force commissioned a feasibility study for a nuclear-powered version of the BR-36 bomber. The result was a vision of nearly unlimited endurance. Pilots could remain airborne for days, maintaining constant readiness. Intelligence officials saw in it the ultimate deterrent, an aircraft that could loiter at the edge of Soviet airspace indefinitely. Congress, too, was intrigued. The Atomic Energy Commission allocated new funding, and by mid-decade the project consumed hundreds of millions of dollars annually. Test reactors were authorized at the Idaho National Reactor Testing Station, a remote, high-desert facility far from cities or populated areas. There, under secrecy, engineers built full-scale mock-ups of nuclear jet engines, each one a step closer to flight. The scientific community was divided. Some hailed it as the pinnacle of atomic progress, others warned of a nightmare. Physicist Ralph Lapp wrote that a nuclear aircraft is an airborne Chernobyl waiting for gravity. Yet in the optimism of the 1950s, such warnings were often dismissed. Nuclear power was the future, and the United States was determined not to let the Soviets claim it first. In this environment of rivalry and ambition, engineers believed they were building a triumph of science. But as the program advanced from theory to metal, a darker realization began to take shape. They weren't just designing an engine that could power flight indefinitely, they were creating a flying nuclear reactor, one that would carry its radioactive heart through the open sky. The promise of endless endurance was real, but so were the invisible dangers that came with it. By 1954, the desert of eastern Idaho had become the unlikely front line of one of America's most ambitious scientific pursuits. A remote expanse known as the National Reactor Testing Station housed a complex of experimental buildings, concrete bunkers, and thick-walled test cells. Here, amid the sagebrush and isolation, General Electric's engineers began assembling what they called the Heat Transfer Reactor Experiments, or HTRE, a series of prototypes designed to test whether a reactor could truly power a jet engine. The first of these, HTRE-1, was unlike any other machine ever built. Instead of burning kerosene, it relied entirely on nuclear fission to heat the air that passed through its turbines. At its core sat hundreds of slender fuel elements containing uranium, each carefully spaced to allow airflow while maintaining critical mass. The design was both elegant and terrifying, a controlled nuclear chain reaction directly coupled to the mechanics of jet propulsion. Construction began in 1955 under tight security. Engineers worked from behind thick viewing windows, manipulating remote cranes to assemble radioactive components. The reactor was mounted on a movable test stand flanked by heavy lead shields. Two modified J-47 turbojet engines, the same type used on the F-86 Sabre, were attached to the reactor outlet ducts. The entire setup looked like a cross between a power plant and a spacecraft. When the system went critical for the first time, the results astonished even the skeptics. As the air compressors came online, the reactor core heated rapidly, reaching over 2,000 degrees Fahrenheit within minutes. The turbines roared to life, their exhaust shimmering faintly blue. The nuclear-powered jet engine had become a reality. Data from the run showed that the system could produce sustained thrust without burning a drop of fuel. It was, in every sense, the first working nuclear jet engine in history. But celebration soon gave way to concern. The airflow exiting the engines carried traces of radioactive particles, xenon, krypton, and iodine isotopes, formed by the fission process and released into the exhaust stream. Though the radiation levels were small, they were measurable. The air inside the test cell became contaminated, requiring remote ventilation and decontamination procedures. Technicians could not enter for hours after each run. The very act of testing proved that while nuclear propulsion worked, it also spread invisible contamination with every second of operation. Still, the momentum of the Cold War kept the project alive. The Air Force's Wright Air Development Center continued to push for a flight-ready engine. General Electric's engineers responded with HTRE-2, an improved design using more durable fuel and refined neutron moderators. It was built to simulate higher power levels and longer endurance. The second prototype operated successfully through 1956, producing higher thrust and greater efficiency. Yet the problem of radiation persisted. At Oak Ridge National Laboratory, another team took a different path. Their project, the Aircraft Reactor Experiment, ARE, sought to avoid the contamination issue by using a molten salt reactor. Instead of solid fuel rods, the ARE used liquid fluoride salts containing uranium-233, which circulated through the reactor core at over 1,500 degrees Fahrenheit. The fluid acted as both fuel and coolant, transferring heat to an air loop that simulated jet propulsion. When the ARE achieved full power in November 1954, it demonstrated remarkable stability. For 100 continuous hours, it ran without incident. Scientists marveled at its potential, high temperature, low pressure, and excellent heat transfer. Some began to imagine molten salt reactors powering future space vehicles or compact power plants. Back in Idaho, the practical challenges of shielding and control dominated the agenda. A reactor powerful enough to propel a bomber required immense shielding to protect the crew. At least 25 tons of lead, steel, and boron carbide plates would be needed to reduce radiation inside the cockpit to safe levels. Every added pound, however, reduced the aircraft's payload and range. Engineers were trapped in a paradox. To fly safely, the aircraft had to be too heavy to fly efficiently. To evaluate these problems in real conditions, the Air Force commissioned an experimental aircraft, the NB-36H Crusader. Derived from the massive Convair NB-36 bomber, it was modified to carry a 1 megawatt reactor inside a heavily shielded compartment. The cockpit was encased in a protective shell of lead and rubber, and the canopy consisted of 10-inch thick lead glass. Even the control cables were routed through shielded conduits. The reactor itself was not connected to the engines, it existed purely to study radiation exposure during flight. In 1955, the NB-36H took to the air for the first time from Carswell Air Force Base in Texas. During each flight, the onboard reactor was brought to criticality as the plane climbed to altitude. Instruments throughout the fuselage and wings measured radiation leakage, while air sampling pods collected data on the plume left behind. Between 1955 and 1957, the NB-36H completed 47 flights, covering nearly 215 hours in the air. The data revealed a sobering reality. Although the shielding protected the crew effectively, radiation leaked into the aircraft structure and surrounding air. Ground personnel were required to undergo decontamination after post-flight inspections. Even though the reactor was small and operated at partial power, it still left detectable traces of radioactivity along the aircraft's flight path. Meanwhile, General Electric moved forward with HTRE-3, the most advanced reactor in the series. It featured improved fuel geometry, more efficient control rods, and a compact, self-contained power system. HTRE-3 represented the final evolution of the concept, a fully functional nuclear turbojet system capable of sustained operation at near-flight conditions. When it ran successfully in 1958, the technical achievement was undeniable. But within the laboratories, a quiet unease spread. Radiation monitoring reports grew increasingly grim. Even with additional filtration and shielding, the test cell remained dangerously hot after each run. Instruments detected airborne fission products escaping into the exhaust stack despite elaborate containment measures. The engineers who had once viewed the project as the future of aviation began to realize they were building something far more hazardous, a power plant that could not be safely operated in open air. At the same time, the program's cost was mounting. By 1958, the Aircraft Nuclear Propulsion Project had absorbed more than $1 billion, an astronomical figure for the era. Critics within the Pentagon began to question whether the potential benefits justified the expense. The advent of intercontinental ballistic missiles, ICBMs, was rapidly changing strategic doctrine. A missile launched from a hardened silo could reach Moscow in minutes, faster and more reliably than any bomber, no matter how far it could fly. Inside the AEC's technical division, health physicists circulated reports warning that even a single crash of a nuclear-powered aircraft could contaminate vast areas with radioactive debris. Cleanup would be nearly impossible. One memo described the potential aftermath of a reactor-powered plane breaking apart mid-air, fuel elements dispersed, fission fragments airborne, contamination across hundreds of square miles. Still, the Air Force resisted abandoning its dream. The Pratt & Whitney indirect cycle reactor remained under development, using liquid metal as an intermediary to transfer heat to conventional jet engines. In theory, this would eliminate direct contamination. In practice, the design grew unwieldy, a labyrinth of pumps, pipes, and heat exchangers too heavy for flight. Yet the engineers continued, driven not only by orders but by genuine scientific curiosity. The project had pushed materials science, reactor physics, and turbine engineering into new territory. They tested high-temperature alloys, neutron-resistant ceramics, and remote handling techniques that would later become vital to civilian nuclear power. Each problem solved spawned two more, and each experiment brought them closer to the uncomfortable truth: nuclear propulsion could work, but it might never be practical or safe. By the late 1950s, General Electric's Idaho facility had become a small city of scientists, machinists, and health monitors. Work continued around the clock. The HTRE-3 reactor, sealed behind multiple barriers, roared intermittently as technicians observed from reinforced bunkers. On the other side of the country, Oak Ridge prepared designs for the Aircraft Reactor Test, ART, a molten salt derivative that promised cleaner operation, but it was never built. As the decade drew to a close, optimism waned. The data was clear: nuclear engines could provide virtually unlimited range, but they would also emit radiation continuously, even in perfect operation. Every flight would leave a faint radioactive wake across the sky. The dream of the endless bomber, once a symbol of American supremacy, had become a radioactive paradox. In the control rooms at Idaho, the men who had shepherded the project from its birth began to understand the full implications. They hadn't just built an engine that could run forever. They had created something that blurred the line between aircraft and reactor, a machine that turned the atmosphere itself into a part of the nuclear cycle. By 1958, the nuclear aircraft program had reached a crossroads. After a decade of experiments, the results were undeniable: nuclear propulsion worked. Yet the same data that proved its feasibility also revealed its fatal flaw. In the test records from Idaho's Heat Transfer Reactor Experiments, radiation readings spiked every time airflow increased. The faster the engines ran, the more fission products appeared in the exhaust. Xenon, krypton, iodine, the signature of nuclear decay. The engineers realized with quiet dread that the exhaust of their engine was radioactive. Inside the control room at Test Area V, health physicists watched Geiger counters flutter wildly after each reactor run. Even when containment doors were sealed, microscopic traces of isotopes escaped through ventilation systems and clung to the walls and instruments. It was no longer just theory. That flying reactor wasn't a metaphor, it was a literal description. Any aircraft powered by this engine would leave a faint radioactive trail in its wake, a signature visible not to the eye, but to radiation detectors hundreds of miles away. The implications were catastrophic. Even a minor mechanical failure, a cracked turbine blade or leaking seal, could spread radioactive material into the sky. Maintenance crews would need robotic tools to replace parts, since no human could approach the engine after operation. The dream of a limitless flight endurance had collided with the limits of physics and of safety. Meanwhile, global politics were shifting. The Intercontinental Ballistic Missile, ICBM, had changed everything. The Atlas and Titan programs, each capable of delivering nuclear warheads across continents in minutes, rendered the notion of a nuclear-powered bomber strategically obsolete. The Air Force could now strike targets without pilots, without refueling, and without risk of radioactive fallout from an accident. At the Pentagon, enthusiasm for the nuclear aircraft project began to cool. The Weapons Systems Evaluation Group, newly established to assess such programs, issued a blunt conclusion in 1959: aircraft nuclear propulsion is neither necessary nor practical in the present strategic context. Their report cited not only the radiation hazard but the staggering cost, more than $1 billion already spent, with no airworthy prototype in sight. General Electric and Pratt & Whitney offered revised designs. GE proposed a more compact, better shielded system with advanced moderators and air filtration. Pratt & Whitney pushed its indirect cycle reactor, which promised to isolate the radioactive core from the jet exhaust using a heat exchanger. But the designs grew heavier and more complex with every safety improvement. Engineers joked that if the plane were ever built, it would need nuclear engines just to lift its own shielding. Even the project's most ardent supporters began to question its future. In a confidential memo, one Air Force official admitted, "We have achieved the physics of flight, but not the practicality of war." The Air Force's vision of a nuclear-powered bomber circling endlessly above the globe was no longer a deterrent, it was a liability. Then came the political reckoning. President Dwight D. Eisenhower, increasingly skeptical of overextended weapons programs, slashed ANP's funding. Only limited reactor tests would continue, mainly for research purposes. The administration diverted resources toward more immediate technologies, ballistic missiles, nuclear submarines, and reconnaissance satellites. For the men at Idaho and Oak Ridge, the order felt like an epitaph. Years of work, innovation, and risk had culminated in a paradox: success that could never be used. Their engine worked exactly as designed, and that was the problem. It was, in the words of one project physicist, a perfect system for the wrong planet. By 1960, the final test logs were written. The engineers shut down the HTRE reactors one last time, their blue glow fading into darkness behind concrete walls. In the silence that followed, it was clear that the age of nuclear flight had ended before it ever truly began. When the Aircraft Nuclear Propulsion Program was formally cancelled in 1961, it marked the quiet end of one of the most audacious experiments in aviation history. The decision came not with ceremony, but through a short line in a Defense Department budget directive. After more than 15 years of work, thousands of personnel, and over $1 billion in research, the project that promised endless flight was over. The last test reactor in Idaho was shut down, sealed in concrete, and left to cool in silence. President John F. Kennedy, briefed on the findings, saw little justification for keeping it alive. Intercontinental ballistic missiles had already made nuclear bombers redundant. And while submarines like the USS Nautilus had proven nuclear propulsion safety at sea, the same principle simply could not be made safe in the air. The idea of a flying reactor was no longer a bold experiment, it was a strategic hazard. The enormous NB-36H aircraft, which had flown dozens of test missions carrying a live reactor, was dismantled at Carswell Air Force Base in Texas. Its reactor compartment was transported under heavy guard to Fort Worth, where it was later encased in concrete and buried at a classified storage site in New Mexico. The rest of the airframe was scrapped for parts. For decades, no official photographs of the reactor bay were publicly released. At the Idaho test site, the HTRE facilities were mothballed. The reactors themselves, HTRE-1, HTRE-2, and HTRE-3, were entombed in place, their radiation levels still measurable through the 1970s. The massive concrete test cells and rusting control bunkers remain today, ghostly reminders of an era that sought to conquer the atom in every domain. Yet the legacy of the project was not lost. The data collected during the ANP years shaped much of modern nuclear and aerospace engineering. The study of high-temperature metals, zirconium hydride moderators, and compact reactor shielding directly influenced the design of later reactors for submarines and spacecraft. NASA's NERVA project, a nuclear thermal rocket program begun in the 1960s, drew heavily on ANP's research in fuel element design and heat transfer. What began as a quest for a nuclear bomber quietly evolved into the foundation for deep space propulsion. For the people who worked on it, the memories were complicated. Some recalled pride in pushing the limits of science, others remembered the unease of walking into hot zones that remained radioactive for weeks after a test. Declassified health reports from the Atomic Energy Commission show that most workers received radiation doses within what were then considered safe limits, though modern standards would classify some exposures as high. The long-term medical monitoring program continued for decades. Publicly, few Americans ever knew the program had existed. Most details remained classified until the 1980s, when fragments of the history surfaced in declassified AEC summaries and defense audits. When the public finally learned of the nuclear airplane, it sounded almost like science fiction, yet the truth was far stranger. The United States had indeed built a working nuclear jet engine, and then buried it before anyone ever saw it fly. The Soviets, too, pursued their own version, Project Tu-119, a modified Tupolev bomber with an onboard reactor. It ended for the same reasons: weight, contamination, and the growing dominance of missile technology. Both superpowers had reached the same conclusion from opposite sides of the Iron Curtain: the nuclear-powered aircraft was technically brilliant but strategically obsolete. By the end of the 1960s, the world had moved on. The skies once imagined to be filled with atomic-powered bombers were instead patrolled by refueled jet fleets and satellites. The idea of a nuclear aircraft faded into a curious footnote of the Cold War, a vision too ambitious for its time. Still, the lessons endured. The program taught the limits of engineering in the face of physics and human safety. It reminded both nations that not every breakthrough should take flight. The dream of boundless power, it turned out, was bound most of all by the responsibility to contain it. Today, in the wide desert of Idaho, the remains of the Heat Transfer Reactor Experiments still stand. Massive steel cylinders, sealed behind chain-link fences and warning signs, rest beneath decades of dust and silence. They are monuments to a time when science seemed limitless, when every boundary could be pushed, and every danger rationalized in the name of progress. To walk among them now is to stand inside the ambitions of the atomic age itself. For the engineers and scientists who once gathered there, the dream had been pure. They weren't building a weapon, they were chasing endurance, the idea that humankind could soar above the limits of fuel, gravity, and distance. In their eyes, nuclear flight was not madness but destiny. Yet the very success of their work revealed its flaw. They had achieved what they set out to prove: a reactor could power an aircraft. But in doing so, they had also created something uncontrollable, a machine that could never operate without consequence. The story of the flying reactor is more than a forgotten Cold War experiment. It is a study in the tension between imagination and responsibility. It shows how progress can outpace wisdom, and how technology often teaches lessons its creators never intended to learn. The scientists who built those engines didn't fail, they simply reached the edge of what humanity could safely command. Decades later, when engineers revisit the data, they find not folly, but foresight. Every boundary defined by the nuclear aircraft program became a warning etched into future designs of what must never again be risked in pursuit of power. As the desert wind sweeps across the Idaho plains, the rusting test cells remain silent, their purpose long concluded. But their presence still speaks. It reminds us that mastery of the atom is not measured by how far we can push it, but by knowing when to stop. History often remembers the triumphs that changed the world. Yet some of its most valuable lessons lie buried in the projects that never took flight, the ones that proved not only what could be done, but why it should not.